Hello, this is Desmond Aubrey from Rarefied Technologies, Southeast Asia, also shortly known as RareTechSEA. We use that because it's a bit simpler for some of the communications on the internet and social media and so on. So you'll either see the name Rarefied Technologies SE Asia, Southeast Asia, or RareTechSEA. Just to give an introduction about who we are and the kind of capabilities that we have, really. I'm going to go through a presentation and hopefully it does what it's supposed to do at each step. Alright, so just to introduce ourselves. So the first one is a bit of a history on the company. It was originally established in South Africa in 2012 as a Pty Limited. And then we moved back to Southeast Asia in 2014. We're actually based in Vientiane, the capital of Lao PDR. The main reason for that is I've had a long history in Southeast Asia, more than 20 years, essentially Thailand as a base, as well as eventually over to Lao as a base. It's enjoyable, it's very nice and quiet, and we are allowed to do what we do. Just the mission statement, what are we all about? Well, passionate about heat transfer. In some of the postings you'll see I talk about Thermo-Fluid equipment, things to do with the transfer of heat and energy and to do with fluid flows and so on, which is quite complex from a scientific point of view. And then things like brazing. This in fact I was a director, technology director for 4 companies in a group, and part of the process was actually to manufacture brazing of automotive heat transfer equipment. So that would be, your radiators on your cars, radiators for big trucks, things like charge air coolers, condensers, evaporators, all this kind of stuff. And so that really got me into the whole brazing technology side of things. In those days they had a process called knock-a-lock. And then I inherited a technology team that was focusing on a new special particle-based technology, and I'll discuss that more in another forum, but that was called CD technology. And we took that technology from being an idea. It had been patented by a chap that had actually developed the principle. What it was a eutectic aluminium silicon alloy with a coating, a flux coating on it. And this was really very good, but it had never been built before, and so I inherited the team. They'd been struggling for 5.5 years. The parent company had invested a huge amount of money into the South African division where I was the director, and I was a headhunter then to come and fix the problem that they had. And they'd spent an enormous amount of money and been going on for about 5.5 years. They had really high-tech equipment, build equipment, really state of the art, but they couldn't get the process right. So I inherited it, and it took us about 3.5 months to get the whole thing totally re-engineered and stable. And from that we then expanded up to about 13 different products, and then I moved on from there onto copper particle process. Actually, it was called the Cooper Brace process. So I went over to Sweden as a consulting engineer to the managing director of in those days Outokumpu Kopparstrip AB, based out of Västerås in Sweden. And that took me all over the world, and my travels took me through over about 36 plus countries. You'll see a bit about that later, but it took me all over the world. So I became a brazing expert, and we had to develop brazing cycles. I had to convert from a lab scale process that they had into high production. And I arrived at a furnace that was none too happy. It was a new furnace, and it certainly wasn't going to work in the US, in Pittsburgh. And so I got involved there, and I helped to straighten out and bring in some of the know-how that I developed with composite deposition, as in know-how about brazing and particle brazing, and then transferred some of the know-how and experience into the copper brass brazing process, and we had success actually. I remember when we were actually doing our first big brazing show-off in Pittsburgh, my boss at the time, a Swedish guy, he was virtually crying at the end of the line. He put so much into it. When I was brought on board, they had 3 months to get this thing straight. That's why he brought me in. And that we got it straight, and I managed to prove to them they could actually save money over aluminium at the time Now, it's of course the copper price went a bit strange later, but at the time we were competitive. We were starting to make headway. And then, so also I like software development. This is part of simulation is something I've been involved in right from my early days as a young engineer, getting involved. In those days, we didn't have the sophistication we had today, but I had to, simulate processes and then design the exchanges to actually do the job. And I did a lot of work in the bitumen field, bitumen with hot oil, energy recovery, that kind of thing. And then I developed the software and the techniques for that. So that's been a passion for me, and that's carried through into RareTech. So the trick is really to identify key technologies, find the source where you can, acquire technologies, build in research, explore, see what's going on, fix it where it's wrong, develop new techniques and so on, package it all together and then implement the technology. And a lot of my base essentially has been industrial, then moving into automotive, and then onto manufacturing. But I've had a huge amount of experience all over the show. And you'll see later I've done some work. I'll talk a bit more about the copper brazing side of things as well that I did. I did a project back in South Africa. We were the first in the world to actually do copper foil brazing. And there's some tricks with copper and copper that are different to copper and brass, and people don't really realize that. So I've developed technology that manages that process, and it actually did very well. They were actually really nice products that came out and have a lot of potential in the HVAC industry with the right partners and so on. Alright, so that's just a little bit about that. And then next screen, heat transfer. What are we talking about here? We're talking about plate heat exchangers and also brazed plate heat exchangers, but essentially the core of it is the plate heat exchanger side. Now that can be single phase, obviously condenser, evaporator, getting all that right. And you'll see I've actually got technology. I've got software we call RTCalc, which we acquired some years ago, but then I've actually then improved and modified to do these kind of simulations. Automotive heat exchangers, that's my game. I know them very well. And I did a lot of consulting at one stage in Thailand to a first tier supplier, and we got very accurate results at the end of the day. Things like HVAC, I've done heat pumps, all kinds of things, but again using the expertise and then figuring out the technology and getting it right. And you'll see some of the what do we call it, some of the presentations, running over words. Some of the presentations you'll actually see that on compact heat pump developments. Modular shell and tube heat exchangers. This is technology that when I started out as a young engineer, I went into the industry, got very involved in petrochem, and then went over to a small company for the love of designing heat exchangers. And I'll talk more about that when I discussed the presentation on modular shell and tube heat exchangers. But they're fascinating because you can create all types. You can start with a single module and make up to like a 48 module if you like, clip them all together. Very, very interesting, very useful technology. And then fin tube heat exchangers. This is where you get different types of fin tubes. Some are like a rolled fin onto the tube. Then you also get these things called block fin, which is like a fin array, and the tubes are then put through. But the trick is to get the fin tube bonding to be correct. This is very important. Otherwise you lose heat transfer. You get effectively a surface resistance if you're not careful. And then mining, a lot of interest there in the elution process, where we use these modular shell and tubes, and where I discussed modular shell and tube technology in that presentation, I talk there about the elution process. In the talk there about the elution process, and where you were involved with effectively an interchanger or economizer, which heats the incoming fluid up, and then what's left behind, the residual, you then have to heat up with a heater, which can be steam or hot oil driven, goes through the elution tower, comes back through the economizer, and then drops the temperatures down sufficiently that you actually don't need an exit cooler or to the electrowinning cell. So we save a lot of money. And I did a study on that lifetime of that process, very interesting, which I've put a paper together on. You can download it from or purchase it from my shop on my website. You can have a link to that. It'll give you a lot of insight actually into how these things actually worked in practice. And then heavy industrial, that kind of thing, whether it be heat exchangers or you name it, I've been involved in all of that. Stationary gen sets, also optimizing those, getting them to work properly. In petrochemical heat exchangers, I've got software and a lot of know-how on how to design. Certainly the Thermo-Fluid side, I don't do all the mechanical design. I can leave that to others. They can do a better job than me. But the basic thermodynamics, you've got to get it right. And often if you get fluids that are mismatched in flow rates from the, let's say, the tube side to the shell side, and if you don't get it right, you can end up with massive units, and units that typically can foul very quickly if you're not careful. So the main, let's call it capabilities that we have: consulting, advising, helping you to go through and give you some wisdom as to what you're seeing. Often people think they get it right, but they don't. So I often help. Sometimes a client might even do a design. We have the same software, and I'll say, right, you do the design, and then I'll just work a design check and a design tweak and an optimization, which I often do, and get a bit tighter than they can do it, and so they get a better product, and it's also probably less expensive for their client as well. Designing from first principles, plenty of that. Rating, in other words, given a certain size unit, and then seeing what it can do. And see if it will do it or not, Things like manufacture, I can advise on the manufacturing. At one stage I was directly involved in manufacturing, but not here, not out and loud. Software development, lots of. I also access access to various external developers as well, who often help me on bigger projects, tricky projects. And then research, I do a lot of research in heat transfer, understanding what's going on, keep adjusting, and also research into new technologies. For instance, the AR technologies are becoming very interesting actually as to what you can do with them. Testing, how to set up tests, what's involved and all of that. Experimental rigs, some ideas on that. I can help a lot with that. In fact, I came across a very interesting technology years ago over in Sweden, a colleague who's now departed, on 3D modeling of a plate heat exchanger, plates, actually fast, quickly getting an answer. CFD, done a lot of work in this. I have a personal project where I'm involved in trying to understand what's going on with fluid turbulence, and I did that. I actually registered at a university in Thailand, and eventually went out on my own just with the research phase on trying to understand the wave nature of the Navier-Stokes equations. These are the partial differential equations that explain incompressible fluid flow. Fascinating actually, and that's all simulation and visualization. And then optimization, that's my game. I typically take something and better it and tweak it. And here's an idea of the kind of stuff that you can do with a good CFD, computational fluid dynamics. I mean, here for instance is a dimpled plate heat exchanger, but actually it can also be a tube array, where you've got an array of tubes, and they're inside a duct, and then you come in over here at the inlet, and then you actually watch what happens to the fluid flows between the dimples or tubes. And do you get flow breaking up and bifurcation, as they call it? What happens to the flows behind it? And you can compare different arrays. And I've actually got more work that I've been publishing up on YouTube on some of these simulations, and they're fascinating. It's fascinating to actually see how some work well and some don't work well. And the thing that's of interest too is to also look at the bypassing that occurs here, where we get no heat transfer on the edge between the tube. This last bit here is a waste of. So what we try to do is get the tube as close, or we can put in bypass strips and a few little tricks to do a better job. But that you can simulate, So it's quite fascinating. A little bit about what I get up to, and then let's see if it'll go on to the next. There we are. And brazing. All right. So what kinds of brazing? Aluminium. Very comfortable with that. I think in American you might call it aluminum. All right. Now that I've spoken about this composite deposition technology, or CD technology, very special process. It had never been done before, but very innovative, and it had it had a lot of challenges, because you're dealing with particles, and you've got to attach particles to a surface. It's tricky, and so the particle sizes are important. With aluminium, you have a problem in how small you make the particle, because you know that rocket fuel sometimes they used to use solid fuel aluminium, So you've got to be careful. There are limits, and so we were working with all of that, and we would then get in the powder which was made offshore, and then we would actually work with that. In the early days, their production was all over the show, so we eventually had to get everything nice and slick. Otherwise, it did affect our final end product, our scrap rates, if you want to call it that. So, and there's also things like binders involved there, and how do you contain the binder, and what happens if you're not careful and it goes into the brazing zone. So I developed a lot of technology and optimized that, and I've kept that pretty much to myself. I've never let that out to other people as to how it actually worked. So that's available. If people want to buy that know-how, they're welcome, and then we can discuss it, and I'll help you come up with some really interesting. And I actually applied the same technology to copper-based processes, and actually end up with beautiful brazed products, so shiny. They were astoundingly shiny. People didn't expect that. So this whole concept of particle brazing technology, you've got to know what you're doing. Particle sizes, how to apply it to the surface. You get problems, you get void problems, void factors. In other words, if you end up with the particles too big, you end up with a lot of gap in between. Now the particles are sitting on a surface, you braze. When it brazes, the particles melt, and they collapse down to a low layer. And all of a sudden, if you're not careful, your actual product starts to fall apart because you've got gaps. So you have to know how to fixture, and dynamic fixturing is very important. And that was quite new for a lot of people, and we had some massive particle stack-ups, and so we had to be able to deal with some really big, let's call it oversize, and we had to pull it all the way back in. Very interesting. And then you get some components where we have like condensers, and the side rails don't bend as much, so you've got quite a challenge. But we got on top of all of that. And then there's things like fluxless brazing, where you can, in this particular case, you don't need flux at all, which is cute. And then knock-a-lock, which is the standard aluminium technology, where you have a clad layer, aluminium silicon clad, eutectic clad, which then basically melts under heat. But they've got to spray these things with so much flux, and flux, too much of that, and it's not very, from an environmental point of view, it's not the best in the world, because it's a fluoride-based flux, So, and it also makes the product not so nice, and they say it gives it a coating layer, but I think you end up with corrosion issues as well if you're not careful. So copper-based, again, this concept of cupra braze, what was that? That was copper and brass, where you had a special anneal-resistant copper fin. This was developed in Sweden. Very, very interesting development, because normal copper, when you apply heat to it, it softens, it becomes so soft you can just throw it around. But they developed this special copper fin, which was trick. There was a lot, basically a certain metallic particle in there, which would then stiffen. Under heat, it would then migrate and stiffen the matrix, and you ended up, when they would actually sing those fins, if you knocked them with your hand, you could ding ding ding. Whereas aluminium, they just collapse, they're very soft. And then a brass tube. This is again an anneal resistant brass tube. They had an additive that they put in there which locked up the brass under heat. It basically locks up at the grain boundaries and stiffens the brass. So for the tube, and then for the header and for the side rails and so on, you have this kind of brass or variants of it. But again, when you've got brass, remember brass is copper and zinc, and then so now you've got zinc in there, and then how do you braze with a certain amount of zinc? Zinc is it basically causes trouble. It's a de-wetting agent, so we had to manage a lot of that certainly on the headers. The tube to headers were very tricky. When I first got onto that project, the tube to header joints, they didn't have any, and so they were trying to back expand and bring them all back to big, they had Americans that a design where they expanded the things out. I said, that's silly, you can't do that in practice, it's just too slow, and it's silly. Let's get the brazing right, which we did. I built a team, we went together and we brazed trial until we got the right mixtures. And then I've got the own process that I've developed, which is for copper to copper. Again, just as you have problems with brass and zinc, copper tubes, in this case what we had is the same anneal resistant copper fin, but with multi-port plain copper tubes. And once you've got a plain tube, you've really got to be careful with your brazing profile, because you don't want to end up with your tube softening too much. So I developed tricks on that and how to do it. This was a special multi-port tube that they developed in South Africa. Really very slick. And I see they've tried to develop elsewhere, and they haven't had success, mostly with copper, because of the amount of energy, and it's very abrasive. When you work with copper as a manufacturer, it's abrasive to your tooling, and it hammers the tooling. So there was a crowd in the US, one of the universities had tried, and it looked very promising, but the energy consumption was amazing, and the production rates I was looking at, in fact, getting a license for it, but and to commercialize it, but it really, I don't think, was worth the effort. So there is space in this market for manufacturers of these multi-port tubes. Technology has moved on, but the actual products themselves, and if you look at some of my copper work, it's really amazing. So the technology I used here was a little bit different to copper braze, in fact quite a bit different, but it actually worked very, very well. So it holds a lot of promise for the HVAC industry. Alright, and the next one is this thing about software development. Okay, so I've been involved in this game certainly from the plate heat exchanger research side since about 1987. Plate heat exchangers kept everything secret. It was essentially most of the let's call it the main development came out of Sweden. So I made a trip over to Sweden to go and visit, actually, with what I call the plate masters, the people that had worked for some of the big names over there. And I spent a few weeks there, and made some friends, but also it got a lot of know-how. And eventually I managed to acquire the rights to software that had been developed out of there. And my colleague there has since passed on, but he was very, very knowledgeable. And so the technology has a long base, a long history, deep history in this game. And then we moved on to things like big data methods. There was a project where we actually took existing software, full of original manufacturer software, and we fired data through it and shot out answers to this, and then analyzed what was going on. And I found a big fault, actually, a fault in the plate heat exchanger methodology, the design methodology, and it boils down to two different methods of understanding heat exchanger design. They arrive at the same answer, but if you do it the way they do it for plates, you miss something important. And I managed to pick up on that by doing a lot of research and going back, trying to really understand what is going on, and then simulating, and eventually I realized, okay, I've got it. And I found a way around that and how to improve so that you get a much tighter selection. Otherwise they get selection all over the show, and then they end up with this huge over surface, and then they say, well, that's fine. Well, it's not, because they fell and they're not very efficient. Cost a lot of money for nothing. Bad design. Whereas the shell and tube, we can tweak that. We can adjust the shell carefully. We can control the tube carefully, and then we can actually adjust the shell side, certainly with modular shell and tube, to get a very accurate mix between the two. And then we use things like machine learning, which is fascinating. You can actually take inputs and then put them against the outputs, and you learn, and eventually you can predict new outputs just by putting in inputs. It's a lovely technology, and that then leads right on to things like the new AI technologies that are emerging. This is amazing, some of it actually. And then I've written quite a few academic papers, given them typically at international conferences. Again, different areas, different tricks. Geometry reviews I find very interesting, looking at what people are doing. Performance prediction software, as I say, I've got a range of, we call it RTCalc, performance prediction software, certainly for plate heat exchangers, but I can also develop for other technologies. And then comparison of new installations to see which one would be best or not. And then world-class software developers. I've actually got guys all over the show that I call on when I need them. Sometimes you have a conversion project and it can be quite tricky to get it right, so I look for the best guys out there and then pull together a team for that particular project. That's a story on its own, actually, managing software guys. All right. And then that's a bit about me. I did a Bachelor of Science and then specialized in engineering and then mechanical. So Bachelor of Science means I have a physics background. We were trained essentially as physicists, and then we specialized over into engineering and then fine-tuned that down into mechanical engineering. But my passion has been what is essentially a hybrid between mechanical and chemical engineering. And this is the heat transfer game. So both faculties cover it, but certainly the mechanical folk tend to handle heat transfer. It seems to be more so than the chemical folk. And that's how I got involved in that. And in the early days, we didn't have a speciality for thermofluids, but I think today some universities may offer that. And I've been working towards a PhD. I've done all the coursework, and I'm working on dissertation. But that's based on understanding the fluid turbulence. I work in the range. If you're an engineer, typically when we design, we have two major design areas. We call laminar flow, which is treacle-like, honey type flow, or you can have the other side, which is like completely mixed up whatever, and we call that fully turbulent. But there's a zone in between that they call the transition zone, and that transition zone, nobody knows anything about it. So they say to you, don't work there because we can't understand it. We have no equations for it. And that's the area I work. It's actually a wave area. And once you understand that, full turbulence effectively is broken waves. And once you understand it that way, it's not so complicated. So I've been a specialist for nearly 40 years now, and had an immense amount of experience. Heat exchangers, heat transfer, that's my game. Brazing, I've said the aluminium and copper. Heat pumps has been fun because it's a challenge. I developed a very, very compact range of heat pumps that I took over to South Africa. Some of them were in Australia too, and I had them built for me in Southeast Asia, and they were actually very, very good, to be honest. Very compact. I was trying to see how small I could go. I mean, in reality, I've got technology that can put a heat pump in your hand if you like. So it's all possible. And then software development, yes, since 1982. This modular heat exchangers that I was referring to, I actually wrote the original software for that, and all the designs thereafter, and it stayed right through. I actually came back to the company and bought it years later, and they've used my software and modified it, and things like heat transfer applications from a software point of view. International travel, at one stage I traveled through over 36 countries all over the globe. I've been too much. So basically I've backed off a bit now. I'm home based, and I consult from home where applicable and focus on the support side of it, not the traveling so much. I've got friends who I send out if necessary to do the pinch hitting, setting up of plant and that kind of thing. And then contact details, that's me. It's me, my contact is in Aubrey, that's my phone number. You can get me direct, or you can use WhatsApp, it's cheaper. And then email, that's my direct email. And Twitter, you can get me at this, as well as also on YouTube as well. I'm starting to put quite a few YouTube videos up there to start to bring in the friends and connections so they know where I am. And then this is just a bit of fun, trying to show you, in this case, the velocity magnitude, okay, in a flow field. Now in this case, as I said earlier on, you've got tubes or dimples, and these are set on a triangular 60-degree triangular pitch, all right? And what's important to the designer is how close should they be together this way, and how close should they be together that way, and what will the flow effect look like? In other words, what are your velocities? Of course, velocity will imply pressure drop. So at the end of the day, you're trying to optimize how much heat transfer you can get versus the amount you're going to pay for, which is pressure drop. And with this kind of thing, you can start to see, all right, fine, I'm getting flow going. It's actually bifurcating. When it hits the next tube, it breaks up and goes between them. But I always worry at the back here. You see, I'm getting heat transfer there, but I'm not getting much happening here in terms of flow. So it's a bit of a dead spot, really. Could I get that dead spot down a bit so I can actually get a better heat transfer, or could I get more wrap of that velocity around that tube? Okay, that's important, is to understand that. Also, can I minimize the wasted flow here? Because there's nothing, this is the edge of the heat exchanger, it's just waste. So you're not getting you're wanting to get the energy into the tube or through the dimple. So, or through, if it's a plate, it goes through the other side. So the areas of high velocity are what you're looking for, but in this case I don't really want to waste energy down the edges, so I can then also experiment to bring the tube closer to the edge. So I've got techniques to do that, and I use software that's fairly straightforward, and so with some of them you just change the geometry, so it depends what clients are looking for. I can do studies in these areas for them to help them optimize, and then say, okay, this is a better one than that, you know. And I tend to be quite quick. I don't mess around with with fancy stuff. I actually do it quickly and come out of the result, also based on experience. You see, the old days we would take something like this and we'd have formulas based on actual experimental work that was done in a wind tunnel or something like that, and then we didn't know all these flow patterns, we just guessed them, to be honest, in the old days. But you ended up with an overall heat transfer coefficient based on the number of tube rows and blah blah. But now you can actually see it, and then some of the work that I do, I actually show, for instance, temperature. What happens if you're putting this temperature in here? What does it look like further down by having a certain control temperature on these tubes? What is this fluid that's getting cooled, what does it look like further down? So we can do all of that. It's trick, but that's also fun. So that's just a bit about who we are and a bit about me mainly. And we've set up a small operation here out in Vientiane. I have a partner who then does the day-to-day admin and various things and runs the bank accounts and does that kind of stuff. So, and there's me. And so that's it. And I really look forward to meeting with some of you out there. Whoever ends up watching this video and needs a bit of help, give me a shout. I'm pretty good at what I do, and I enjoy doing it, and I enjoy sharing it with people out there, especially when I go over to other countries. Well, I used to go over to other countries and often go and lecture India, all over. I've been to Thailand and lecture on various things in heat transfer, but that's my game. So anyway, thank you so much for your time. I hope you find it interesting and I haven't bored you too much. Okay, I'll say goodbye for now. Cheerio. Bye-bye.